All right. Good morning, everyone. Welcome back. Hopefully, we've had enough time to absorb all the previous information. We're going to pick up right where we left off as promised with C and D from 1.3. So that won't take too long. They will be probably they'll obviously be more complicated than A and B because they're going to introduce a concept I mentioned in the instructions, but we hadn't seen one yet, where we have a variable written twice and we actually have to factor it out. So spoilers there. And then we'll immediately get into 1.4. And we will be finishing both of these sections today, which means they will both be due in on 1 week from now by 11:59 p.m., which will be February 2nd. So please, please, please ensure that you complete the homeworks in time. Again, 1.3 and 1.4 will be finished today, which means their homeworks are due in 1 week. Remember, that will be the policy unless I state otherwise for some reason at some point in the class. Our first test will be covering chapter 1. It's still going to be quite a while before we finish chapter 1. Some of these later sections are a little longer. 1.5 we will not finish in one class. Just as an FYI, that's a really long section. So I'm still not going to say what the test date is, but we've got a few weeks away. And remember, I said I will always give you at least 1 week's notice. But let's not waste any more time. Let's go ahead and get right back into it. And as usual, I'll be in the chat in a couple of minutes if you have any questions.
Let's go to draw. C. So what we were doing when we left off a week ago was these literal equations, also known as formulas. So we said that we're going to handle any variable that's not being solved for as a constant. It's just you're pretending like it's a number. You're not actually going to make it a number. You just pretend. You move it away from the variable you're trying to solve for. So when there is when there is more than one of the variable being solved for, you will likely have to move it to the same side and factor it out as a GCF. And then this blue ink right here was just showing us how, all right, if you have 3y plus 5y, those are like terms, you can combine them and make an 8y. CLT, combine like terms. Pretty traditional, it's what we usually have. But this is what we're going to start seeing, something like an xy plus an ay. They both have a y, but you can't say x plus a is, I don't know, 43.7. You can't tell what x plus a is. So instead of adding the numbers, because these aren't really numbers, they're not like terms, you just take that common factor of y out and then you factor it. So you take it out and then it's like you divided each of these terms by y. So xy divided by y is x, ay divided by y is a. If you don't trust this answer right here, if you distribute the y to the x and the a, you will get the original left-hand side. But again, the point is to distribute it in this instance. A lot of the times in math, what we want is what we don't have. So that's going to be very important for C. Here was A and B. P equals 2L plus 2W. We solved it for L. There was only a single L, so we kicked the 2W over by addition or subtraction. And then we saw nothing really happens here. You just leave it as P minus 2W. You don't even focus on that. So when I'm figuring out what to do next, I don't even look at what that was. I'm only looking here and saying, well, that's 2 times L, so we got to divide both sides by 2, and that's what we did. And then I showed you the other version of this. If you split it up and go to those notes to review if you're rusty. Then we did another one, solving for D. It was the only D, so we moved this B over by subtraction. Then we divided the C and the E out to get the answer. So for problem C, that issue that I scrolled up to earlier with the GCF stuff, that's about to happen. Spoiler alerts. So let's go. I don't want that color. That is not the color I want. A equals P plus PRT. And we're going to solve this for P. Now, if I solved it for R or T, this would be a very different problem in terms of difficulty. It would be simpler. But solving for P, switch this back to red. There's a P here and a P here. There's 2 of them. So that issue that was mentioned before has finally come up. First of all, they need to be on the same side to factor it out as a GCF, which they already are. Spoilers for the next problem, they won't be. So once they're on the same side, you can just say, hey, I've got a GCF of P. So I'm going to take that P out. I'm going to put a parentheses around it. And then inside, is where that division is going to go. So I'm saying, all right, P divided by P. That's how factoring works. You're dividing it out. So P divided by P is 1. If you don't trust that, remultiply. P times 1 gives you this P. And then plus PRT divided by P is RT. Basically, this is what you're doing in your head. You're dividing it by P like that and saying those cancel. If you need to show that work, undo, please. Undo, thank you. If you need to show that work, you can. But that's essentially what you're doing. You're just dividing by P here, dividing by P here. But that division is us saying the P is going out as a product. And then the left-hand side is still just an A equals. Now we're supposed to be solving for P. I said last time that one thing I like to do is circle the letter being solved for. So in the original one, I would have circled these two and said there's 2 of them. So combine like terms or factor, whichever was necessary, in this instance factoring. Now I only see one displayed. That's much nicer. And this is P times something. This right here is similar to having A is equal to P times 5. If you had that, you would divide both sides by 5. Just P times a number, so you divide by the number. And what we're doing is we're pretending that all these other things are numbers. 1 plus RT, this parentheses is just some number. And it's a number multiplying by the P, so guess what? We divide both sides by 1 plus RT. Divide both sides by 1 plus RT. Some people will put it in a parentheses like this, and that's okay. It is optional because there's nothing else in the denominator. So I'll leave it in the simpler looking form like that. And we're dividing so that those cancel. Remember, I tend to undo showing my canceling, so show that in your own work if you like, but I don't want it in my permanent notes. So then what that gives us over here, I don't know why I keep, no, that was good, that was good. A over 1 plus RT equals P. Again, these have canceled, they're gone now. So the right-hand side is just the variable we were solving for. Is this a pretty answer? No, but is it the answer? Yes. There's no way you could split this because the plus is in the bottom. You can't split fractions when you have pluses or minuses in the bottom in that way. You can only split them when they're in the top, like the answer to B as well as A. So the answer to D, I'm sorry, I'm looking at this D and I said D. The answer to problem B, you could have split this fraction like we did with A. See, in A, we split it up as 2 fractions and we said, hey, here's an alternate form as an answer, but both were fine. I could have split this one in the same regard, but I can't split this one because the plus is in the bottom, not the top. All right. Finally, my favorite of the bunch, which of course you know means probably the most challenging. A plus D is equal to DE minus B. And we're going to solve this one for the letter D because there's 2 of them. The rest of them would be much easier to do because there's only 1 of them. If you wanted to solve for A, you just you'd subtract D on both sides and you'd be done. If you wanted to solve for B, you could subtract DE and then divide by -1 and you'd be done. This problem's a little more involved because there's a D here, excuse me, and there's a D here. There's 2 of them. So we're going to have to apply that same principle we did in the last one, but before we can even do that, there's a problem. We said we need that variable on the same side. These D's are on opposite sides of the variable. Excuse me, opposite sides of the equals. So you will likely have to move it to the same side and factor it out as a GCF. So that's what we're going to do here. Does it matter if I move the terms with the D's to the left or to the right? Honestly, it does not matter. For a reason I am going to go with that I'm not even going to explain, I'm going to move them to the right. So this is the way I'm going to do things. I'm going to subtract D on both sides. And I'm going to put it under this term DE, and this is written kind of poorly. And I also want it to be in red, not blue, because I'm going to use blue for everything else after this. So what we will get is A. Now these D's are gone. So A is the only thing on the left side for now, equals DE minus D It looks like dead, D-E-D. You can't combine those because this has an E and this does not. In the same reason we couldn't combine the P and the PRT last time. But there's still that minus B over there. Now, this term has got the D, this term has got the D, so that's where we're going to take it out as a GCF. But we don't want anything else on that side. So these two terms have a D, but this one does not. So what we want to do is now move all non-D terms to the other side, which means we need to add B to both sides. Again, I'm choosing to write this in somewhat poor form because I know most people do anyways. A plus B does not make C or Q, it's A plus B. The DE minus D is still there. These minus and plus B's cancel. This is the ideal scenario. This is where you want to be. You want all the terms that have the variable you're solving for on one side, and any terms that don't have the D on the other side, because that means we can take out our GCF finally. See, when the B was here, you couldn't say there was a GCF of D in all these terms because it's only in the first pair. And it would just look a little wacky to leave the minus B there. So our GCF is D. So we get A plus B equals, we factor the D out. When we take when we take D from DE, we would be left with the E, and there's the minus symbol. When we divide D by D, we get 1. Don't leave this blank. Don't do this and just do E and a space or a 0 or anything like that. It's E minus 1 because we're taking the D from this D, we're dividing it, and anything divided by itself is 1. So be careful here. Be careful with that. That's where people make silly mistakes. Now all we got to do is that one more step. This is D times some random number, whatever E minus 1 happens to be. So let's divide by the E minus 1, giving us our answer. And it ain't pretty, but that's perfectly fine. A plus B over E minus 1 is equal to D. Actually not the only form of the answer. This one can be split into A over E minus 1 plus B over E minus 1. See, I'm not splitting across the bottom sign, I'm splitting across the top sign. So this is an okay answer as well, but there's really no reason to split it because neither of these things reduce. It's only when something would reduce that it's really beneficial to split it, which is why I didn't show you that work in B previously either. So this is okay, but this is the better answer because it's less work to do. All right, so we did those. So there we go. 1.3 is now complete. You may notice in the homework there's 1 or 2 types of application problems that I did not cover in this course, in the lecture. That is not the point of lectures in math, to cover every single type of application, believe it or not. Now maybe in a lower level, but in a pre-calc level, we're supposed to use logic and reasoning and other things that we've seen to try and challenge ourselves in different situations. So you might notice a geometry problem involving the perimeter of a rectangle. We didn't do any of those, but just remember that the perimeter of a rectangle is 2L plus 2W. I even gave you that formula as part of an example. That was an intentional reminder right here. But just note that you may see 1 or 2 types of applications that I did not cover, but remember there's this in the homeworks that are generally there. All right, so let's move on to 1.4. They're called complex numbers. Just give myself some space. Social distancing in my Word file, if you will. All right, complex numbers. This does not mean complicated numbers. And you may have heard something called the complex fraction, but some teachers will call it a compound fraction, was actually a better name for it. I prefer the name compound fraction because compound fractions don't actually have complex numbers in them. So calling it a complex fraction, it's kind of a misnomer in my opinion. They're just saying complex fractions are complicated. But right here, these complex numbers, it's not that they're complicated. In theory, they are. The idea is definitely complicated. But what we're getting into is the idea that, so in the past, if you had, say, the square root of 4, you'd say that was equal to 2. But if you had the square root of negative 4, you would say that was, you may have said it does not exist, or you may have said it's not real. The does not exist part is kind of a lie. Some teachers will just give you these little baby lies in lower level classes because it's not important at that point. But the not real, this is the better answer in the previous math classes. You will never say this though at our level because that's as in the past. Now, how are we actually doing things? What's the point of this? So the square root of 4 is 2 because 2 times 2 is 4. But the square root of negative 4, in terms of what we call the real number set, we would say is not real because you can't come up with a number and multiply it by itself that gives you negative 4. And you might say, well, why not do negative 2 and negative 2? Because negative 2 times negative 2 is positive 4. Say negative 2 times negative 2 is positive 4. You might say, okay, we'll try positive 2. 2 times 2 is also positive 4. But the negative is what we have to have. And some people might say, well, why can't you do 2 times negative 2? Because that's not how square roots work. They have to be the exact same number. So that's why originally we say the square root of negative 4, we don't worry about, it does not exist, quotes, which is not really true. The better answer is, again, it's not real. Every number that you have discussed with me thus far in this course has been a real number. 5, square root of 7, 3, negative a million, pi. Those are all real numbers. What we're going to start getting into are what we call the, which you should have discussed in your previous classes, unless you're here and shouldn't be, your imaginary numbers. Now, I always get as a student every semester that goes, why are we studying imaginary numbers? Why are we doing fake math, fake news, right? Here's the thing about math. The names are awful. They're almost always awful. Calculus is the study of change in math. If you go into dentistry, you know what it is? It's the study of the gunk between your teeth. Rational numbers in math means fractions, but in the real world, it means, rational thoughts, kind of like logic and reasoning connecting the dots. Radicals in math means these square roots or cube roots. In the real world, it's surfer lingo, right? Or California lingo, at least, whatever, West Coast, Best Coast. So the name imaginary number is a poor name. It's not that these numbers are fake. It's not that they don't exist. They do exist. The name imaginary has to do with what we call their roots or their x-intercepts. And we'll discuss that idea when it becomes more relevant. So what we are going to do is we are going to define base imaginary number. Right now, we are creating something. We're defining this. This is what some mathematicians said hundreds of years ago. They said, this square root of a negative, this pops up in science and engineering all over the place. If you just say it doesn't exist, this world wouldn't exist. The waves in the ocean have to do with square roots of negatives. When you're talking about forces in different directions, they have to do with square roots of negatives quite often. It's everywhere. So what do we call it? I don't want red for this. What just happened? Why are you doing this to me? Thank you. That's all I wanted to do. All right. The square root of -1. Sorry for that. Technology is fun. I missed the whiteboard. Is equal to I. I like to do my eyes a little curly on the right side, personally, just so they don't end up looking like ones if my dot's too small. So we have literally just said the square root of -1 is I. This is the base imaginary number. When you get square roots of negatives in this class, don't you ever say it does not exist. Don't you ever say it's not real. You're going to be turning them into I's. So, oh wow, that was loud. Trash man's coming by. Sorry for the distraction. It's a fun day. So, the imaginary numbers along with the real numbers make up what we call the complex number system. So any complex number, not complex hashtag, any complex number can be written form A plus BI. And again, that I is the same I you see over there, a little curly I. A is what we call the real part, lowercase a. And then B is what we call the, you might guess it, the imaginary part. And again, it's not that these things don't exist. They absolutely exist. It's just a different type of numbering system that we have entire fields of mathematics based on. In fact, every single number that you have dealt with in this course and in previous courses has been complex. Every single number in the world, complex. So the complex numbers have real and imaginary parts. So far, we've only dealt with real numbers, but real numbers are complex. Do you know how a real number is complex? You just make the B 0. So A, which is a real number, it is complex. It's just that B is equal to 0. Also, BI is complex. It's just that the A is 0. So imaginary numbers are complex, real numbers are complex. Every number in the world is complex. So real numbers are what we call a subset of complex numbers. Imaginary numbers are a subset of complex numbers. And what I mean by subset is, here's our complex. Numbers are here. You can say that our real numbers are here. And our imaginary numbers are here. Okay, so question. Does it matter if the variables are in caps or lowercase? No, it does not. Keep the I lowercase. You don't want a capital I, it just looks kind of weird. I've never seen a mathematician do it that way. I'm not saying it's technically wrong. There we go. So that was a good question. Now, here's the cool thing about the imaginary number system along with the complex number system. All the rules that we've learned are pretty much the same. How to add, subtract, multiply. It's basically just with adding and subtracting, combine like terms. With multiplying, you may have to distribute, you may have to FOIL. You'll end up adding some exponents here and there. Division's a little wonky, but we'll relate that to something else that is a little wonky in its division. But we'll get there after some examples. Before we get to the actual adding, subtracting, multiplying, dividing things, for example 1, what we're going to just do, simplify some square roots. For A, we'll have the square root of -4, which we will no longer say does not exist or undefined. We will say, hey, the square root of -4, what you want to do is break this up as a product. And ultimately, you probably won't have to do this, but here's what I get most students to do at the start of this concept. Write -4 as 4 times -1. Because we know the square root of 4, and we now know what the square root of -1 is. We chose to define it as this guy right here, or girl, whatever. Doesn't matter. So with square roots of products or quotients, you can take the square roots individually. So you can do the square root of 4 times the square root of -1. This doesn't work with sums or differences, just products and quotients. And then the square root of 4 is 2. And we've just said, hey, square root of -1, we're just going to call an I. So 2i is the answer. That's it. So if you took 2i times 2i, you would end up getting -4. Why is that? We'll see after 2 more examples. But that means that 2i times 2i is -4. Now, do you need to show this step and this step? Not necessarily. It depends on your skill level. I've got plenty of students that for this problem would go straight from the far left black ink to the far right blue ink. And as long as it's correct, I don't care if you're not showing that 1 or 2 steps worth of work. All right, B. Let's do another one. And we're going to do the square root of negative 50. We're going to step this up a notch. So again, if you're going to take the long road, it's a good idea to write this as a product. Maybe write this as the square root of 50 times negative 1. Well, last time we had, and you can do this extra step if you really want to, square root of 50 times square root of negative 1. Last time the square root of 4 we were able to take as 2. This time we don't really know the square root of 50. We know the square root of 49 is 7. We know the square root of 64 is 8. So the square root of 50 is between 7 and 8. But it's an irrational number. It's going to be like 7.23, blah, 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 blah. And that's not what I'm asking for here. So what we're going to do is the same idea before. Split this up. You can't do this for every number, but if the number can be split up into a product where one of those is a known square root, then that's how you want to do it. 50 you could write as 5 times 10, but I don't know the square root of either of those. You might say to write it as 1 times 50, that's completely pointless always. But if you did 2 times 25, we know the square root of 25, so let's do it like that. So we're going to do the square root of 25 times the square root of 2 times the square root of negative 1. I just went ahead and split those into separate square roots. If you left that under one radical and then did this step, that would be fine. But again, it's the same idea as going from here to here. So this 50, I'm now saying is 2 times 25, which 2 times 25 is 50, so that's perfect. Where we know the square root of 25, it's 5. We don't know the square root of 2, so let's leave that alone. And we know the square root of 1, we have chosen to define that as I. So this would be 5 times the square root of 2 times I. Now this is a technically correct answer, but I'm going to suggest that you don't leave your answer this way. So this is okay, but this is the better way to write it. The 5, then the I, then the square root of 2. This is better. Let me show you why that's better. Now again, my math lab would count this correct. I would count this correct, the one that says okay. But this is just better, and you might say, well, that looks weird because the I is sandwiched in between them. Don't we like the I at the end? Usually we like the I at the end. But in this instance, here's what can happen. So this would be wrong. Here's what some people will do. They'll go 5, square root of 2, and they'll put the I in this. See, this I is not supposed to be in the square root. It's supposed to be beside it. That square root was supposed to have ended before we got to the I. I have seen countless people, students or teachers, do this. Now there are square roots of I's. That's way outside of our pay grade. We're not going to discuss that. But that's what can go wrong when you leave it this way. That's why I say it's better to do it this way, especially in my math lab where you probably are hitting the right arrow to get out of the square root. If you don't do that, then your I is going to be inside like the red version, and it'll be wrong. All right, C. Let's do another one. One last one, and this one will keep you on your toes. This is the cube root of negative 27. Now that's a cube root. That's a different thing than a square root. It's a different process. We're not trying to come up with a number times itself to make negative 27. We're trying to come up with a number times itself times itself. We need to have it multiplied and have 3 of them in total to make negative 27. So here's what a lot of people will do. They'll do A and B and they go, I got this. I know that this is going to be, I'm pulling out the red ink. This is negative 3 because 3 times 3 times 3. I'm sorry, what did I do that? Not negative 3. They'll say that this is 3i. They'll say that it's 3i because they have a radical with a negative, and they'll say, well, that's because 3 times 3 times 3 is 27, so we have a negative inside, so just slap an I on that and you got your answer. And this is wrong. I may have already spoiled the answer. I may have not. I've got a lot of inflection in my voice, so you might already know what I'm trying to get at. But this was wrong because it's not a square root, it's a cube root. We never had a problem in the past. We never had a problem in the past with cube roots of negatives. It was square roots of negatives that we had a problem with because a negative times a negative was a positive. When you have a cube root of a negative times a negative is positive, and then times another negative makes it negative. This answer is actually just -3 because, and let me get off red because it's no longer wrong. Sorry about that. So that's because -3 times -3 times -3 is -27. There are no imaginary numbers needed for cube roots. Now, if we did a fourth root, you can't take a fourth root of a negative, but the thing is, it's not I. The fourth root of a negative does not involve an I. There's something else, and again, this is another case where it's above our pay grade. Don't worry, you won't see that in this course. We will only deal with square roots of negatives, and in those instances, and this kind of sounds gross, pull out an I. So remember, when you have a square root of a negative, not just any root, only a square root of a negative, you pull out an I. When you have odd roots of negatives, they can still have answers, but any other even roots of negatives would not have answers for us. But again, I won't even ask you any of those in the class, so it's irrelevant. All right. So let's go back to the main definition. So if the square root of -1 is equal to I, semicolon, that's not a J, that's a semicolon, what is I squared equal to? Whenever we see a square root of a negative, we now pull out an I. We now write an I. Don't you ever write a square root of a negative again in your math classes ever as an answer to simplifying some value. But this issue is going to come up very, 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 very often. Earlier I said, all right, the square root of -4 is 2i, which means 2i times 2i is -4. Well, 2i times 2i ends up being 4i squared. The 2 times 2 gives you the 4, and the I times I gives you an I squared. Well, it turns out that every single power of an I can be turned into one of only 4 numbers. It's called a cyclical group. That's the fancy math term for it. It's got some really cool implications. So like I to the 3rd power is the same as I to the 7th power is the same as I to the 11th power. Every 4 powers have the same answer. I squared is the same as I to the 6th is the same as I to the 10th. We don't have any reason to study anything past I squared at our level, so that's where we'll stop. But it's still cool knowing that. I'll even tell you what the other 2 are, but you won't need it. So what is I squared? Well, what we can do is we can take the square root of -1 is I. Let's take our definition. These 2 things are equivalent. Let's square both sides. So whatever we do to one side, we're doing to the other. So -1 squared equals I squared. The reason I squared both sides is because I now see an I squared. These steps like this feel like, why am I doing this? How did I know to do this? Because we've been doing this for hundreds of years. The challenge is learning how to figure out these things on your own if you're a scientist or mathematician. You got to try a million things before you get the right thing that actually works, the right process. So now we see an I squared, so if we can simplify the left side, then this is good enough. Well, we can definitely simplify the left side because we know, we've been saying in this class a little bit so far, that square roots and squares cancel. Square roots, and that's an ampersand, and squares cancel. Just like cube roots and cubes cancel. So all of this is going to cancel itself out basically, and we're just left with the inside, which is -1. So -1 is equal to I squared. So this red right here is for emphasis. So what we have is, whenever you see a square root of a -1, you turn that into an I. Whenever you see an I squared, you turn that into a -1. Those are the only 2 powers of I you need to know. I will verbally say, that's a redundant statement, I cubed is negative I, and I to the fourth is positive 1. I cubed is negative I, and I to the fourth is positive 1. And you can actually find those in the same manner as what we just did. Not necessarily squaring both sides each time, but by multiplying both sides by an I, or squaring maybe the I squared equals negative 1. If you square this, you'll get I to the fourth. If you square negative 1, you get positive 1. So I to the fourth is positive 1. Alternatively, if you just took this and multiplied both sides by I, you'd get I cubed on the left, and you'd get negative I on the right, and that's it. All right, so example 2. Simplify. Once again, get back to black. We got 3 plus 5i in parentheses plus 6 minus 3i in parentheses. Now, I've done something here that I don't really like doing for me personally, but I like to show the students. There's a plus sign here. Plus signs in front of another parentheses do nothing. This is literally the same as 3 plus 5i plus 6 minus 3i. There's absolutely no reason for these parentheses to be here because of this being a plus, and there not being anything in front of either of the parentheses. All right, so what do? This is just combined like terms. You're just pretending these i's are x's. 3 plus 6, those are like terms, that's a 9. 5i minus 3i, well 5 minus 3 is 2. You just leave the I there, so that's a plus 2i. That's the answer. Yes, it is okay to write 2i plus 9. This is okay, but the complex number system, we usually like the real part first, then the imaginary part second. Again, it is not wrong to write 2i plus 9. That's why I said this is okay. It's just better to write 9 plus 2i, real than imaginary. And again, don't get caught on that idea of imaginary numbers. We will show you eventually why they're named imaginary. Same pair of numbers, 3 plus 5i and then 6 minus 3i. But this time we're going to subtract them instead. Let me just clean that up. There we go. Now this time, there's a minus between the parentheses. That means at least one of these parentheses was necessary. The first one isn't. The first one is not necessary. It doesn't do anything for us. That could have just been 3 plus 5i. I'm about to write it. But with the minus in front of the parentheses, that means you need to distribute it. This is where people make their simple mistakes. Nobody's perfect. I've done it before myself. But that should be a minus 6, and then not a minus 3i, but a plus 3i now, because this negative and this negative cancel each other out. Combine your like terms. 3 minus 6 is negative 3. 5i plus 3i is a plus 8i. And yes, 8i minus 3 would be okay, but I'm not going to keep writing those alternate forms. Next up, same pair of numbers, 3 plus 5i. And I bet you can guess what I'm going to do. If I went plus and then minus, then 6 minus 3i. So this one you're going to have to FOIL. First, outer, inner, last. So first is the 3 times the 6. 3 times 6 being 18. The outer is the 3 times the negative 3i. 3 times negative 3 is negative 9, so that would be a negative 9i. Again, those i's are acting just like x's essentially, but they're not variables. Then the inner would be the 5i times the 6. 5 times 6 is 30, so that's a plus 30i. Then the last would be the 5i times the negative 3i. 5 times negative 3 is negative 15. But the I times the I is not I, it's I squared. This is where people make other simple mistakes. I times I is I squared. Now you've got two different issues right here. You've got like terms, minus 9i and 30i. Those are like, so you can combine them. And negative 9 plus 30 would be positive 21. Remember, I do expect you to be able to handle sign math in this class. No calculators for test 1. So that's 18 plus 21i. And I'll see some people stop here and write just minus 15i squared. I'm not going to write the I squared though. And again, if you did, you might think that's the answer. You got a constant, an I, and an I squared. But we just said we never, ever, ever leave an I squared in an answer in this course. I squared we will always turn into negative 1. So that's what we have to do here. So this will be times negative 1. So this I squared is negative 1. You will see that repeatedly, which makes that last bit 18 plus 21i plus 15, negative, negative, which is 18 plus 15 is 33, then plus 21i. Some people will stop with the previous. They'll stop here, but the 18 and the 15 are alike. You got to make sure you catch that. You got to combine them. D, and we're going to finally switch the numbers. You might think I'm going to do a division next, but I'm not. And I like that idea, but we need to introduce an idea. 3 plus 4i times 3 minus 4i. I'm going to put a little asterisk next to D because this one's important. This problem is going to play an important role for division. There is something special about these parentheses being multiplied. These two things are the same basically, 3, 4i, 3, 4i, but one of them's a plus and one of them's a minus. They have to be this setup. It can be minus and then plus, but they have to be opposite signs here. It can't go plus and plus, it can't go minus and minus. One has to be a plus, one has to be a minus. There's a special name for these, I'll give it at the end. But let's do this, we're gonna FOIL it again. So the 3 times the 3 is going to give us a 9. That's the first. The outer, 3 times the negative 4i would give us a negative 12i, so minus 12i. The inner is 4i times 3, which is also 12i, but this time positive for the inner. The last, 4i times negative 4i, would be negative. 4 times negative 4 is negative. 4 times 4 is 16. Then the I times the I gives us I squared. The negative 12i and the positive 12i, these are like terms, so we're going to combine them. But they're very special like terms. They are opposites of each other. They will cancel. The negative 12i and the positive 12i cancel each other out. That is the entire point of this product and what we're going to use leading into the division version. The fact that the outer and the inner cancel. Whenever you have this setup, this a plus b times a minus b, the outer and the inner will always cancel. So there is no I term. This is just 9, but we still have that minus 16, but we know I squared is supposed to be negative 1. So don't write I squared, write times negative 1. If you're able to go ahead and make that a plus 16, skipping that step, that would have been perfectly fine. That's 9 plus 16, which is 25. Look at the last set of answers. 9 plus 2i, negative 3 plus 8i, 33 plus 21i, versus this answer, 25. These were complex in that they had both real and imaginary parts, so they were real and imaginary. This 25, while still complex, it does not have an imaginary part. It is completely real. And that is exactly why we need this type of problem for what we're about to do. So problem D right there really sets us up for what we're about to do. Sorry for the gap here. But when we have what we call A plus B, lowercase a, plus bi, and A minus bi, these are called complex conjugates. These are called complex conjugates because we're taking an idea known as conjugates, but throwing an imaginary number in them, so we call them complex. So this is versus a plus b and a minus b being called just conjugates. So when they have the imaginary term in there, we call them complex conjugates. When they don't, we call them conjugates. Here's the cool thing. If you call a plus bi and a minus bi conjugates, no one's going to argue with you. That's still right. They're conjugates that happen to have complex numbers in them. But remember that factoring formula, the difference of squares, a plus b times a minus b is a squared minus b squared? It is that thing that enables, again, this big, beautiful, your answer is a real number. So because a plus b times a minus b is equal to, and I'm going to write this part in pen, a squared minus b squared, when, this makes the outer and inner always cancel. So there's no I term. And the I squared term, stop uppercasing. I know you think that's proper English. I squared. The I squared term will always become a negative real number. This makes the answer real. So that's the logic and reasoning behind this. Because we're multiplying conjugates, the outer and the inner will drop out because they're like terms. The outer and the inner would have held the regular I term. The last term is going to end up having an I squared, and I squareds become real numbers as well. So this will always give us a real number. Now, what's the point of this? The point of this is to divide complex numbers. There's literally no way to divide complex numbers. You can't do it. It's impossible. There's a couple times you can simplify due to special cases, but you cannot literally divide complex numbers, just like you can't divide radicals. And if you remember, this complex number is defined as a radical. So when you're doing complex math with these i's, you are actually doing radical math. So all the rules that apply to that apply here. And there was a rule for dividing radicals, which is exactly the same as this, but with square roots instead of i's. So to divide complex numbers, multiply top and bottom complex conjugate of the bottom. This will make the bottom a real number ultimately. That's all we're really worried about. The standard complex form is a plus bi. That means there's no I squareds in answers. There's no I cubes in answers. There's no i's in denominators of answers. And the reason we can't have i's in the denominators is because we can't have square roots in denominators. So this dividing of complex numbers means multiply top and bottom by the complex conjugate of the bottom. This is the exact same thing you do with square root problems. And those topics were in your prereq material, your review material. So we're borrowing from the idea of doing something like this. 3 over 2 plus the square root of 5. If you had this and you were told to simplify, you can't divide by the bottom that way. You have to multiply top and bottom by 2, minus the square root of 5. The conjugate of plus is minus, so that's why we do that. And then you would just continue on, and ultimately you would have a whole number in the bottom with no square root. I'm not going to finish that problem. you're more than welcome to on your own. But that's the idea we're borrowing from, rationalizing the denominator with square roots. The reason we borrow that idea is because i's and square roots are literally the exact same thing. So now we'll be in example 3. Are we on time? 20 minutes. Simplify. And we'll do 2 of these. For A, we're going to have 4 over 2 minus 3i. So I got an I in a denominator, which means I have to go through with this process. Multiply top and bottom by the conjugate of the bottom. So we're going to multiply top and bottom by the conjugate. All it means is take all these terms, the 2 and the 3i, but change the minus to a plus. So 2 plus 3i in the top, 2 plus 3i in the bottom. We're not pulling this out of thin air. I have explained exactly why we're doing this. Because this product in the bottom is a guaranteed real number, because when you multiply things of this form, they always turn out to be real numbers, like we saw in example 2D. All right, so 4 times 2 in the top is going to be 8. 4 times 3i in the top, 4 times 3 is 12, so that's a plus 12i. Over. In the bottom, we're going to FOIL. The 2 times the 2 is 4. If you're rusty with your foiling, go practice 100 of them. For the outer, the 2 times the positive 3i is a plus 6i. Again, that was the outer, the 2 furthest away from each other. Inner means the 2 closest to each other. Watch your signs. That's a negative 3i times a 2, so a negative 6i. Those will cancel. If they don't, we've done something wrong. And then the last is the negative 3i times the positive 3i. Just need to extend my fraction. Negative 3 times positive 3 is negative 9. I times I is I squared. The top is going to turn out to whatever the top is going to turn out to be. 8 plus 12i for now. Over. It's the bottom that must simplify to a real number. If it doesn't, you've gone wrong. Leave the 4 alone for now. The 6i and the minus 6i will cancel, as we said is necessary. The last term was a minus 9i squared, but we're going to change that to a minus 9 times negative 1, because I squared is negative 1. So that's 8 plus 12i over 4 plus 9, which is 8 plus 12i over 13. The bottom is a real number, which means there's no square root, which means this is the answer. Sure, you could split this up as 8 over 13 plus 12 over 13i. That would be perfectly fine. And I'm not going to leave it. Oops, why did that erase? I'm not going to leave this. I am going to erase it. 8 over 13 plus 12 over 13i. This is okay as well. But I want to have that room for the next problem. That's why I'm going to erase it. But you got the video, so you can see it there again. B. I'm on black. 3 minus 4i over 4 plus 3i. So we take that problem. Don't change anything in the original fraction. But we say, okay, we have no idea how to divide complex numbers. Even your math teacher doesn't know. You have to use a trick to get around it. The same way we don't know how to divide by radicals. So we use a trick to get around it. And that trick is the idea of multiplying conjugate pairs, canceling all the crazy things, thankfully. We're lucky that that happens. So we multiply by the conjugate of the bottom. Don't even look at this top when you're figuring out what to multiply by. Ignore it. 4 plus 3i, you just got to make it a 4 minus 3i. So we multiply both top and bottom by 4 minus 3i. Okay, now we're going to have to FOIL the top and the bottom. Again, the top can be whatever it turns out to be. It's the bottom that has a special form in the end. For the top, 3 times 4 is 12. 3 times negative 3i is going to be negative 9i. Negative 4i times 4 is going to be a negative 16i. And then negative 4i times negative 3i would be a positive 12i squared. The bottom, the 4 times 4 is 16. That's your first. Your outer, 4 times negative 3i is negative 12i. Your inner, 3i times 4 is positive 12i. They're going to cancel, so we're doing good. 3i times negative 3i is negative 9i. Correct? Incorrect. I squared. Don't forget that square. Cancel your like terms in the bottom. Combine your like terms in the top. They don't cancel, but they do combine. Turn your I squareds into negative ones. So this will be 12 minus 25i. Negative 9 minus 16 is negative 25. And then the 12i squared, that's going to be a plus 12 times negative 1 now. Over. Leave the 16. Those cancel. The minus 9i squared is a minus 9 times negative 1 now. I'm going to go down here to save myself the space. That's now going to be in the top 12 minus 25i minus 12 over 16 plus 9. This doesn't have to happen in the top, but it does this time. The 12s cancel, and you're just left with a minus 25i. And the bottom 16 and 9 make 25. And this is not an acceptable answer because the 25s are the only thing there. There's no pluses or minuses, so they definitely cancel. And you get a quite simple answer of negative I. The answers don't have to be ugly. They can be simple. And it's very difficult to tell whether the answer is going to be simple or not. Be careful. There's a little memo. Let's say you did a bunch of this stuff and you got to your answer and you said it was, let's say 5 plus 10i over 15. If you said this was your answer, this would be wrong. This is wrong. I'm not saying that I did anything wrong up to this point. I'm saying if I made this my answer, it would be wrong. And that's because there's a factor of 5 in all of these. There's a 5 here, there's a 5 here, and there's a 5 here. Now, if this had been a 6, if this right here had been a 6 instead, this would be an acceptable answer because there's no number that goes into all 3 of these that would reduce all 3 of them. I can't just reduce the 10 with the 15 or the 6 with the 15. You have to reduce them all with the same value. But it's not a 6. It was a 5. So what we can do is take a 5 out of the top and then say that's 1 plus 2i over 5 times 3. And then cancel the 5s like that because then we're factored. And that would just give us 1 plus 2i over 3. Or if you don't want to do the GCF method, what you do is you just take 5 plus 10i over 15, and you just literally divide them all by whatever the common number is. So 5 goes into 5 once, into 10 twice, and into 15 3 times. And it would give you the same answer. But it's only when that factor is everywhere. I discussed this issue in the previous section, in fact, when we were talking about the P equals 2L plus 2W problem when we solved it for L, how you had 2's in 2 of the 3 positions, but because it was in 2 of the 3 positions, did I close it? I did not. Awesome. See right here. See, this 2 is here and here, but there isn't a factor of 2 here. That's why we could not cancel them in this format. If there was a 2p here, if this was there, then I could get rid of all the 2's. So when you have fractions, when you want to reduce them, you have to be able to reduce them in all terms or bring them to a factored form and then reduce out the factors. Now, some people might say, well, I just left the bottom as 15 and then slashed through it and made it 3 in the end. That would be fine too. Get the job done however you can. I've shown you multiple methods. Use the method you're comfortable with. All right, last pair of examples. Example 4, simplify. And be careful of the order of steps. You will have no reason to know why the order is this order, but it's kind of a PEMDAS thing. It's kind of a PEMDAS thing. So 3 times the square root of negative 5, all of that in parentheses, times in parentheses 4 square root of negative 3. there's two things we need to accomplish. We want to have just one real number and one radical number, or sorry, one rational and one non-rational number. So we want an answer something like 5 square root of 2, maybe 5i square root of 2, whatever. The numbers don't matter. It's just that's what we're trying to get. We don't want multiple radicals. We don't want multiple sections of outside numbers. So there's two things we're going to have to do. We see square roots of negatives, so we might be pulling those out and making i's like earlier. And then we have things that can multiply. We can multiply the 3 and the 4. We can multiply the insides of radicals. Outsides can be multiplied, insides can be multiplied, but we can't cross. So those are the two things we have to do, but we have to do them in a very specific order. Red ink for very specific order. You must pull out the i's first. 1, 2, 3, 4, 5 exclamation marks. If you don't do this, your answer will be wrong. I guarantee it. And I will even show you the wrong way for one of them after we finish, assuming we have the time. I think we will. So we can just go ahead and pull out the i's. This is what we must do first. You have to. So this will be 3. And I'm going to skip writing this as the square root of 5 times negative 1. I'm just going to go ahead and pull out the I. 3i square root of 5. Because that would have been the square root of 5 times the square root of negative 1. The square root of negative 1 is I. But I said I like the I wedged in the middle, so I don't accidentally do that and put the I under it. So there's the first one. And then times 4i square root of 3. Whenever you see a negative inside a radical, pull out an I. Now let's multiply outsides and insides. This is not foiling. There's no pluses or minuses separating anything. This is just one product, but we have to do the product outside and then inside. So for the outside, we're taking the 3i times the 4i. 3 times 4 is 12. I times I is I squared. So that was the 3i times the 4i. Then we have our square root. Now multiply the insides. 5 times 3 is 15. Now, if you can do anything with this square root, if you can simplify it, simplify it. But we can't. But this isn't done because I squared is equal to negative 1. So that's 12 times negative 1 times the square root of 15. But that should just be written as negative 12 square root of 15. This is the answer. I will show you the wrong way, and then I'm going to erase it because I know I have time. So if I had said, if I hadn't pulled out the i's first, if I had the 3 square root of negative 5 times the 4 square root of negative 3, multiply the outsides, 3 times 4 is 12. Multiply the insides. Negative 5 times negative 3 is actually positive 15. There's no negative inside of the i's now. That's just a square root of positive 15, and there's nothing you can do to simplify this any further. But trust me, I'm not lying to you. I know you don't know exactly why, but this negative is supposed to be the answer. And this is actually what will happen every time if you do it the wrong way. You'll get the opposite of the correct answer. So again, this was wrong. Do not do it this way. Do not multiply before pulling your i's out. You have to pull the i's out first. It is a PEMDAS type of step. So square roots count as parentheses. I may or may not have said that at some point in our course so far, but square roots count as parentheses. So if there's anything to rip out of them, you're supposed to do that before you go multiplying things. Multiply is step 3, parentheses is step 1. That's the basic reasoning for it. And I know you might feel like I'm grasping at straws, but that's the reason. All right. Uno más. B, and this is going to be 2 square root of negative 8 times 5 square root of negative 2. Spoilers, this isn't a spoiler, I don't know why I said spoiler. These parentheses that I'm writing are completely arbitrary. I don't really need it, but without the parentheses, I would need a dot here for sure. I just like it better with the parentheses. So that's the way I choose to write it. All right, so what do we got to do first? We got to pull our i's out first. Sounds gross, I know. Laugh at it. Or don't, I'm not going to force you to laugh. 2. I square root of 8. I took the square root of a negative out as an I. And times 5 square root of 2. Now you might say, all right, well, hey, the square root of 8 we can break up as 4 times 2. We can pop out the square root of 4 as a 2 and then multiply it outside. And all of that is absolutely correct. And you can do it that way, but I'm going to do this in a much shorter way. And again, what I just said was fine. I am okay with things that are right and not doing it in my order. But let's go ahead and do the same procedure as last time. We pulled out the i's, then we multiplied. And at that point, if we need to break up square roots, then we will. Anyone catch my error yet? I left that open. What did I do? I didn't put an I here. I did that on purpose. Kind of wanted to see if anyone would come in the chat and say it, but that's okay. You might not have caught it because I was rambling. So 2i squared of 8, 5i squared of 2. Square root of negative, pull out an I. Easy to forget. 2i times 5i, that's the outsides. 2 times 5 is 10. I times I is I squared. Then the insides. So we have our square root. 8 times 2 is the insides. 8 times 2 is 16. Well, square root of 16 is 4. I squared is negative 1. So this is 10 times negative 1 times 4, which is just negative 40. And if you did this problem by breaking up the square root of 8 first, you would get the same answer, but you would take more time because you'd end up with, negative 20 times the square root of 4, breaking it up that way ultimately, and then you'd have negative 20 times 2, which is still negative 40. Again, the order doesn't actually matter. We got like 5 minutes left.
All right. So that's going to be it. I actually have like 6 minutes, 7 minutes left. But even still, that was finishing the section. And I know that with 1.3, I did start the section and we only had a few minutes just to type some things up. But I'm not a fan of always doing that. And I don't want to do that with 1.5. So we're going to go ahead and call it a day there. Please remember that. Use my little editing section to get those due dates. That 1.3 and 1.4, those homeworks are going to be due on February 2nd. Yes, so 1.3 and 1.4 due February 2nd, and of course by 11:59 p.m. The 1.2 due date was mentioned in last class. You'll see it in my math lab. It's probably the 28th. I'm pretty sure it's the 28th, but checking that just to make sure. Don't hold me accountable for that, but I'm pretty sure it's the 28th. So besides that, if you have any questions, please email me. We'll pick up right where we left off with 1.5 next class, and we'll do a good chunk of 1.5, but like I already said, we won't finish it, so that 1.5 homework won't be due for another week. Take care, everyone. We'll see you Thursday.